So the next section of our filter discussion basically will be focused on understanding how do we model loss in filters. This is a very important area where essentially it's something we haven't looked carefully so far, mostly because all of our discussion has been on synthesizing lossless filters. So the question is, okay, you synthesize your lossless filter, now you have to deal with loss. How do we do it? So first of all, let me remind you, how do we model loss? And the primary source of loss in filters is actually is found in the resonators. Of course, coupling sections also represent loss. And quite honestly, we're going to ignore that here. This is technically not correct. But in most practical scenarios, it's actually the resonators that contribute the vast majority of loss in a filter. So you'll be, in normal circumstances, quite well positioned if you can just take into account the loss from the resonators. I'm showing you here the two simplest resonators that we have seen. This is the series resonator right here. This is a shunt resonator right here. And each one of them can essentially be associated with a quality factor, which in the past I have called unloaded Q, but you will also find in the literature the term intrinsic quality factor, and so I'm using that here as well. Intrinsic quality factor and unloaded quality factor are basically one and the same thing. So this is the intrinsic or unloaded quality factor for the series resonator, and this is the intrinsic or unloaded quality factor for the shunt resonator. Again, as a reminder, that resistance that you see here could actually be attributed to multiple things. In the simplest possible scenario, this is purely ohmic loss. But usually there are other factors as well that will increase this, and those are radiation, which is an important factor in higher frequencies, and dielectric loss, which is also an important factor in higher frequencies. So keep that in mind, that just by reducing ohmic loss, you're not necessarily guaranteeing that the resistance will be low. Now, a few important things to keep in mind. So first of all, that loss is not constant. The loss in resonators in general tend to increase as a function of frequency, and that means that the higher the filter, the more loss you will have, keeping everything else the same. Specifically, in most microwave resonators, you will actually see a dependence on the square root of f. And that is primarily due to the skin effect. So because the skin effect resistance changes as the square root of f, if most of your loss is due to resistive loss, then you will actually observe that type of increase. Again, unfortunately, other loss factors like radiation will also come on top of what you see basically here. Also, the second thing you should keep in mind is you should basically be careful of the technology you're using to properly reduce loss where necessary. For example, in cavities, and this is a technology that essentially utilizes closed resonators, that means your radiation is practically zero, you need to pay particular attention to dielectric loss, because usually conductor losses are primarily low. So it's not unusual to have a conductor, a cavity base, for example, on copper, and that means your loss will be pretty low. But if you fill the cavity with a poor dielectric, then forget it, it's actually going to be pretty bad. Similarly, for microstrip, the first thing we try to reduce is the conductor loss, the second thing we try to reduce is dielectric, and finally we worry about radiation. So if you have a good modeling tool that basically models your specific resonator, you can essentially estimate this unloaded quality factor. So once you estimate this unloaded quality factor, the second question that we will have to ask is, what is the impact of this on the final insertion loss of the filter? So there are many ways you can do that. One thing that a lot of people find very useful is to very easily estimate that just by using the equation you see here. This equation actually gives you a very quick zeroth order, actually I should say first order approximation of what loss you'll end up with before you actually do anything else. And because of that, it's very, very useful. So for example, if you ask the question, okay, I'm having a Q unloaded of, let's say, 80, that's what I think I will get, and I have to build a filter, let's say at 2 gigahertz, and that filter needs to have a fractional bandwidth of 2%, what kind of insertion loss will I get? You just apply this equation here where this G parameters are basically the G parameters related to the type of filter you want to build. Now, it's true you will not always have the G parameters, but for many cases you will have some G parameters you can rely on. And if you do that, again, you will get a very accurate estimate without building anything, without simulating anything, without estimating anything. So you can very quickly, for example, make that assessment. Conversely, by knowing that somebody tells you, look, your filter must be less than 2 dB, it must be a fifth order Chebyshev or whatever, then you can very quickly extract, oh, you know what, that means my Q has to be above 500, so now you know exactly what technology you have to use for that. And for example, you can't use lumped elements. Now, the second step, once you know the filter area, is essentially how are you going to estimate this more accurately from the coupling matrix synthesis technique. Again, the equation I just gave you is more of a first order approximation, and later on I'll give you examples that basically teach you how accurate that thing is. But there is a slightly more involved, just again algebraic calculations, nothing too difficult, where you can basically make the estimate even better. So we're going to be using these sigma factors that you see right here. And that sigma factor can essentially be computed for every single resonator. If you simply know the intrinsic quality of your resonator, again, the center frequency of your filter, as well as its bandwidth, you can calculate that sigma for every single resonator. And that sigma basically will come into the R matrix that we have already talked about in the past. Essentially, those zeros that used to exist here in the center of that matrix, that was the case for the totally lossless scenario, will now be replaced with that sigma factor for each resonator. Now, in reality, most of the times that sigma is the same for all resonators, because most of the times we basically use the same resonator over and over again. But the power of this technique, as opposed to the previous one that I gave you here, is actually the fact that this one works even if they're not the same. So even if they're not the same, and for whatever reason you decide to use a non-uniform distribution of loss into the system, you can still capture this accurately. Now, once you make this modification for the R matrix, basically the S21 and S11 are computed with exactly the same equations as we used before. Now, there's a second equivalent way, and it's really a matter of taste whether you modify the R matrix or you modify the M matrix for including loss. So if you decide not to touch the R matrix, there is equivalently, you can take the same sigma factors and basically put them in the diagonal of the coupling matrix. Remember that the diagonal, before we discuss loss, used to have these self-resonant, let's call them coefficients, that if you remember from the previous discussion, these are related essentially to the ability to do asynchronous tuning, meaning that you can have an offset in frequency for each resonator, and this is captured by the diagonal element. Now, by putting this negative J sigma in each one of them, you can also introduce loss if you would like. So again, either approach 1 with R or approach 2 with M will basically work. Now, a couple of remarks which I already made mostly, but I wanted you to see them here as well. One is that it's usually the case that you have a uniform loss distribution, but it's not necessarily true, and the coupling matrix does allow you to do the non-uniform loss distribution as well. Later on, I'll say a few more things of why that might be useful.